Hello, welcome back to 15-Minute Math. So we're going to talk about U-substitution today. So U-substitution is a method of finding antiderivatives when there's probably some chain rule involved. So it's kind of just reverse engineering the chain rule, but it's a systematic way to do it. And so what we're going to do is, in our previous video, we were talking about finding an antiderivative for functions that involved e to the something. And we were just kind of guessing and checking, and that's not very satisfying for a lot of people. So we're going to revisit that and then show you how you can use this U-substitution technique to get away from that sort of guess and check thing. So maybe we have an integral that looks something like this. 4x plus 4 times e to the x squared plus 2x, maybe minus 5, and that's dx. So we're going to find the antiderivative of that expression in there with respect to x. And what we were saying in a previous video was, since e is kind of its own derivative, it's also its own antiderivative. So we're just going to guess the e portion of that. And then see how we can fix it. Then take the derivative of it and then see how we can fix it. So, let's take the derivative of this expression. And of course, e is its own derivative. But because of chain rule, we then have to take the derivative of this inside expression, which would give me 2x plus 2. And I kind of see what I've got and what I need, and it seems like to me I need to multiply my original expression by 2, so it's going to be 2 times e to the x squared plus 2x minus 5. Don't forget your plus c, your arbitrary constant. And I say I need to multiply by 2 because I have 2x plus 2 instead of 4x plus 4, so obviously if I just double what I started with, constant multiples aren't affected by differentiation, so that's going to get us where we need to go. But that's not very satisfying, right? Why should I just guess something and hope it works? Obviously, with E sort of things, things aren't quite so complicated, but maybe there's more complicated functions out there, and guessing and checking, it's just not going to cut it all the time. So we need a systematic way to do this, and U-substitution gives us that systematic way. And so here's kind of how we do this with U-substitution. Let's rewrite this integral first of all. U-substitution is most often used when there's a composition of functions. And right now I see this exponential as a composition, right? Because I've got the quadratic function inside of the exponent of the exponential function. And so when I have a composition of functions, f of g of x, I like to think of things as an inner function and an outer function. And the trick is we're going to do a change of variables, and we're going to say, okay, let u equal the inner function, x squared plus 2x minus 5. That's not to say this will always 100% work every time there's a composition of functions. If you just do this change of variables where u is the inner function, it's always going to work. But oftentimes that's the case, and if you don't have a better idea, that's a great starting point. So that's what we're going to do. And before we start going about our business, we're going to want to take the derivative of u. So the derivative of u with respect to x is going to be 2x plus 2. And let's go ahead and multiply through by dx. Okay. And what I like to do is just at this point start swapping things out. This is called a variable switch. So we're going to switch out our variables here with things that we have kind of uncovered down in this area. So first of all, e to the u is going to be, this quadratic is just going to be replaced with u. Now let's look at that. We want to swap out this dx, but I'm not quite ready to do that because I can't just make a straight swap right now because I've taken care of this part of my integral with e to the u, but now I've got 4x plus 4 and dx to replace. And when I'm looking here, if I just put in du, that's going to give me 2x plus 2 dx. I need 4x plus 4 dx. So what I need to do is I need to fix that. So if I would just multiply both sides by 2, I'm going to end up with 2 du equals 4x plus 4 dx. And now I can swap everything out. So it's actually just going to have to be 2 du. And that takes care of the 4x plus 4 and the dx. And now everything's swapped out. And so the idea is this integral here is probably much simpler than the integral we started with, and of course it is. Remember, constant multiples can be moved outside. And e is its own antiderivative, so it's just going to be 2 times e to the u plus c. Don't forget your arbitrary constant. Now the only thing is we really don't care what u is. We want to know what things are in terms of x, so just don't forget to swap back out at the end of the day and switch it back in terms of x. So I like to think about it as in terms of tag team wrestling. It's like you tag your teammate out, you do some stuff, and then at the end of the day you got to tag your teammate back in. And so there we go. So I forgot my plus c. But that's exactly what we got from our guess and check method. But we didn't guess and check. This was very systematic, and there wasn't a lot of room for guessing. Okay, so that in a nutshell is our U-substitution. Let's try another example. All right, so we're going to find the antiderivative of, let's see here, maybe we're going to do 6x over x squared plus 5 dx. So again, I have a composition of functions in that I can think of this as 6x times 1 over something, where that something is like my inner function. And so I'm going to let u be this denominator here. It's going to be x squared plus 5. So our next step is to take the derivative with respect to x. I'm just going to get 2x. And then our next step is go ahead and multiply through by dx. So du is 2x dx. And now we can start swapping things out. So instead of x squared plus 5, I can just put a u. Now, in order to replace the dx, or maybe I should say the 6x dx, I'd like to use this line here, but notice I have 2x dx. I need to fix that. So how do I take 2x and turn it into 6x? Well, we can just obviously multiply by 3. And so I'm going to have 3 du equals 6x dx, which is exactly what I'm trying to replace, so I'm in good shape. And so it's going to be, in order to get rid of that 6x dx, I need to replace it with 3 du. And again, notice what we have now is much simpler than what we started with. Constant multiples can go outside of the integral sign. So this is going to be 3 times the integral 1 over u du. I say integral, I should probably say antiderivative of 1 over u with respect to u. And we know the antiderivative of 1 over u is just going to be the natural log of the absolute value of u plus c, and that's going to be multiplied by 3. Now just don't forget, we really don't care what u is. We really would like to know in terms of x, so this is going to be the natural log. And actually I don't need absolute values here because this expression is always going to be positive. There we go. So that is my antiderivative. And if you don't believe me, just take the derivative, right? You can always check your work on these problems just by taking the derivative of your result and checking that it matched your original, which I have scribbled out, so that's kind of unfortunate. But let's go ahead and let's do it. I think it's worth our while. So constant multiples are unaffected by differentiation, so let's differentiate this natural log. So remember, natural log is 1 over whatever. Then because of chain rule, you have to take the derivative of that function. So in this case, it would be 2x, 5 drops off. Our constant multiple drops off because, of course, constants go to 0 under differentiation. So now we just have 3 times 2x, so we get 6x over x squared plus 5, which is, in fact, what was inside of our integral here to start with, so we must have done it correctly. U-substitution works. Happy day. There we go. So let's try one more example. This time we'll do a trig function. So we're going to find the antiderivative. Cosine of 2x times the sine of 2x dx. And so this is kind of an interesting one. And this is why I kind of want to show you this, because if you follow my advice, just kind of naively, you're going to say, okay, let u equal 2x, then du is going to equal 2 dx. And when we start swapping things out, we're not going to get very far. We're going to have the cosine of u, the sine of u, and I guess in order to fix this, I don't see a 2 anywhere, so we just multiply by a half. And so actually I'll have 1/2 of that du. But that didn't simplify my integral. Like, I'm still in the same position. I don't know what the antiderivative of cosine times sine is. There's nowhere that we've previously discussed how to find the antiderivative of that. So that's kind of a problem. And this kind of highlights one of the maybe frustrating aspects of U-substitution. You don't always have a clear idea of what to let u equal. But here is what I notice. Cosine is the derivative of sine. And when in doubt, let u be not the derivative, let it be the other thing. Let u equal the sine of 2x. And the reason this works is, remember what our next step is going to be. Our next step is to take the derivative with respect to x. So the derivative of sine is going to be cosine of 2x. Now, because of chain rule, times 2. Let's go ahead and multiply through by dx. And so now when I start replacing things, okay, u gets swapped out for sine. And you're thinking to yourself, well, how do I replace the cosine? Well, I've got the cosine here, so I can replace cosine, no problem. I'm just off by an extra factor of 2, so I can just multiply both sides by a half. And notice I'll get this cancellation here. And so now I can swap out the cosine 2x. I can swap out the dx just by putting in 1/2 du. Constants can go outside the integral sign, so I'm just going to integrate u du. I guess I shouldn't lose track of that constant multiple though. And that's a fairly easy antiderivative. We can use the inverse power rule, add 1 to the exponent, divide by the new exponent. This should be 1/2 u squared plus c. I still have my constant multiple to bring down. So really it's going to be 1/4 u squared plus c. Just don't forget to tag back in your teammate, right? We're kind of playing our tag team, swap u in, swap u out. So what was u actually equal to? U is actually equal to the sine of 2x. So we get sine squared 2x plus c. Well, I should say 1/4 sine squared 2x plus c. So again, U-substitution, it works. Sometimes you have to be a little creative with what you let u equal to. But as you get more and more experience, it kind of becomes a little bit more natural of what to set u equal to. Just remember, if there's a composition of functions, you almost always want to let u be like the inside function of that composition. But if that doesn't get you anywhere, you may have to come up with other ideas.